Very good. So I'd like to start by thanking Nazir and Ian and the other organizers for the kind invitation and an opportunity to be part of this very interesting conference. Today I'm going to be discussing work on solution processing of thin film solar cells, and some of the opportunities and challenges that I see in this area. And this is work that really took place at IBM. I was there for 23 years, and I just recently moved to Duke University. And so I'd like to acknowledge the collaboration with a very talented team of researchers from IBM over the years, as well as our joint development partners from TOK Corporation and Solar Frontier, and of course Sunshot for funding for the CZTS work that I'll be describing. And of course my new team at Duke, who's busy right now putting together the lab. And so with this, the focus of the project is to develop low-cost, high-efficiency photovoltaic devices. And in our case, we're doing this by using thin film PV, so looking at the thin film aspect of PV. And we're also focused on abundant or readily available elements. And so today I'm going to start by giving a brief introduction to thin film PV. And then we'll discuss two aspects of solution-based deposition that we've been working on, CIGS, copper indium gallium sulfide selenide, and CZTS, copper zinc tin sulfide selenide. And I'll also very briefly touch on the organic and inorganic perovskites, but I'll very briefly touch on that because of the beautiful talk yesterday and some of the comments today as well that covered that area already quite thoroughly. And so if we look at thin film PV, the market has been growing in this area. So the global supply of thin film PV panels has grown from around 2 gigawatts back in 2010 up to a projected above 4 gigawatts in 2015. Over this time frame, the deployment has shifted from Europe to the US and Japan. In part, this may be the result of incentives. It also turns out to be where the dominant players in this field are based. So First Solar in the US for cadmium telluride and Solar Frontier for CIGS in Japan. And the distribution of thin film technologies has also shifted over this time. So if we look from 2010 up to a projection to 2018, we see that the market share of thin film PV, which are these top components of this graph here, has stayed at roughly around 10%, but the contributions have shifted from amorphous silicon to this newer technology, which is CIGS. And so one question could be, and one of the things that we're interested in thinking about, is are there other thin film technologies that could help shift this market share further toward the thin film aspect of PV. And so with this in mind, we can first take a look at the two dominant chalcogenide-based technologies, cadmium telluride and CIGS. The reason for looking at these is that they offer a number of advantages. They're, of course, direct bandgap semiconductors, so we can use very thin layers. Their grain boundaries are relatively benign with respect to recombination, meaning that we can use polycrystalline films rather than needing single crystal layers and still hope to get high performance. They're compatible with monolithic integration, which again should help lower cost. And they offer the opportunity, because of their thinness and the compatibility with polycrystalline nature, they're compatible with, and also the processing temperatures, they're compatible with flexible substrates. And this opens up opportunities for high throughput processing, which again should be important in terms of lowering costs. So in principle, these are great advantages. There are some disadvantages, namely that CadTel involves cadmium, which is a heavy metal, and is restricted in certain markets. And both these technologies involve elements that are rare in the Earth's crust. So CadTel involves indium, tellurium, and CIGS involves indium. And the scarcity of these elements brings up question as to how scalable these technologies are if we're looking to scale to hundreds of gigawatts. And so for this reason, there's interest in a third chalcogenide technology, CZTS, in which the indium and gallium and CIGS is replaced by the more plentiful and lower cost zinc and tin. And in this substitution, we're replacing one trivalent ion by roughly equal numbers or ratios of divalent zinc and tetravalent tin. And because of the ordering of these ions in the tetragonal unit cell, we get a different space group, I4 bar versus I4 bar 2D, and therefore a different structural type known as kesterite. And so at IBM, we had an interest in focusing on CIGS because of the already demonstrated high performance and the lack of cadmium in the absorber, and also CZTS because of the potential for scalability if the efficiency can be sufficiently improved. And the device structure that we use is standard in the field. We use a glass substrate on which is deposited by generally sputtering molybdenum as a back contact. Then we have our absorber, which is either the CIGS or the CZTS. And on top of that, chemical bath deposited Cad sulfide is the N-type material. This could be also indium sulfide, zinc oxysulfide, etc. And then finally, we have our transparent top contact. In addition to looking at thin film PV, we're also interested in focusing on solution-based processing. And again, this is to reduce cost. And the reason we hope that this would reduce cost is because there's no need for a vacuum. We don't need to evacuate large chambers. There's also not a need for high temperature sources for evaporation, so less energy input during the processing. And in principle, one can get very high throughput for these deposition approaches. In addition, solution-based deposition is very simple. We just take the relevant materials, dissolve them in an appropriate solvent, and then deposit these onto a substrate using well-defined or well-known techniques, doctor-blading, slit casting, spin coating, and ultimately heat treat it. The heat treatment is to evaporate the solvent, perhaps to decompose a precursor, as well as to induce grain growth. The question is, how can we get these relatively insoluble materials into solution? And one approach we've looked at is using hydrazine, N2H4. This is a strong reducing agent, so it enables us to fully dissolve the chalcogenides in the solvent, and we can also incorporate extra sulfur and selenium, which is good for crystallization, and of course these elements are also needed in the final material. And the hydrazine decomposes cleanly, which means that the final films are clean from impurities. Of course, there are issues with toxicity and combustibility, and therefore the hydrazine needs to be used very carefully. But the process is very simple. We just take the starting metals and chalcogens, dissolve them in hydrazine with excess chalcogen. We create this pure solution. And you can see an example of an indium solution here. Basically, for the metals, they react in hydrazine to form these metal chalcogenide anions, and hydrazinium cations, and the solutions bubble, so they give off nitrogen gas. But the main thing is we're getting mixing on a molecular level, and this is important when it comes time for a thermal treatment. It means we can do the thermal treatment quite quickly. We don't need to have long annealing sequences, which will give opportunity for volatile elements to disappear. And so if we take our solution, we can solution process it into thin film form. If we heat it up above 500 degrees C, we can generate our CIGS film with adequate grain structure. Sometimes we don't want to heat up above 500 degrees C. For example, if we want to work with very low cost, low TG glass, or maybe a polymeric substrate. And so we've looked at mechanisms for reducing the heating temperature. And one of these approaches involves controlled incorporation of impurities such as antimony or bismuth. Here we see in this example introducing as little as 0.5 mole% of antimony enables getting a grain structure that extends across the entire thickness of the film, even when processing at temperatures as low as 400 degrees C. And if we look at the depth profile, compositional profile of antimony in the film using SIMS, we find that after the anneal, all of the antimony is collected at the back contact at the moly-CIGS interface. And so the introduction of antimony into this film is not actually incorporating into the CIGS, but is catalyzing the grain growth as it migrates to the back contact. And using this approach, we've been able to deposit devices with efficiency over 10%, even when processing at temperatures below 400 degrees C. And we've also, even when processing at high temperature, still see a significant improvement in device performance by, on average, 2 to 3% absolute when we introduce antimony during the deposition process. And this improvement predominantly comes from the short circuit current in the device, presumably because of better grain structure in the film. So introduction of impurities is one powerful technique for improving device performance. Another approach that we've explored is control over the thermal processing. So in this experiment, we have the same starting solution, same metal composition, same excess of selenium. We're processing to the same final temperature in a rapid thermal annealing tool, but we vary the heating rates from minimum to maximum. By varying the heating rate, we're also varying the effective selenium concentration in the film during the crystallization process. Namely, if we heat slowly, the extra selenium has a chance to evaporate from the film before we reach the crystallization temperature, and if we heat fast, this is not the case. And this has a big impact on device performance. Here we can see slow heating, low performance, fast heating, high performance. And the change in performance is reflected in all the PV parameters, the short circuit current, the open circuit voltage, and the fill factor. And naturally, we'd like to understand where this is coming from, and a good place to start is the quantum efficiency curve. If we look at the long wavelength tail on this and plot it versus energy, we can extract the band gap and see that the heating rate does not affect the band gap of the material, but we do see substantially more suppression of the quantum efficiency at long wavelength, and this is associated with more recombination. And so the question is, where is this recombination coming from? What are the defects that are leading to this issue? So if we look at sim-step profiling, we find that we get the same bulk composition. So this is consistent with the same band gap. However, looking at XPS, or medium energy ion scattering, there's clearly a higher concentration, 2 times higher concentration of gallium near the top surface of the films when films are processed with minimum selenium activity compared to those processed with maximum selenium activity. And since these films are already copper poor, we make them copper poor to avoid the formation of copper-rich phases that can segregate the grain boundary and shunt the device. We consider this gallium enhancement at the surface to be reflective of a higher concentration of gallium on copper defects at the surface of the film under the lower selenium activity conditions. And this is also evident if we look at admittance spectroscopy, which can give you a measure of the trap density as a function of energy measured relative to a band edge. And in the case of maximum selenium activity, there are 2 dominant features, this so-called alpha feature, which is low energy, close to the band edge. This is what's responsible for doping in CIGS, and it's basically the copper vacancies. And then there's this deeper feature, so-called N1 feature, which there are a number of possible origins for this, but one of them is this indium and gallium on copper defect. And as we go from the maximum selenium activity to minimum selenium activity, we see the absorption or reduction in this alpha feature and the enhancement of this N1 feature, which is supportive of this idea that copper vacancies are being filled by gallium at the surface of the film when the selenium activity is lowered during grain growth. And so what I think is important about this is it shows the importance of controlling selenium activity and heating rate during the growth of high-performance films. And so using approaches like this, the antimony doping, controlled heating, also controlling the sulfur to selenium ratio, we've been able to go from 10% devices back in 2008 up to above 15% devices more recently. This shows one of our record device that we made. And so we were very happy with these results, but decided that it would be a good idea to try this approach with other materials. And one of those materials was CZTS. I've already mentioned why. And this is a material that back in 1988 was introduced as a potentially interesting PV material by Ito and Nakazawa. In 1996, Katagiri demonstrated the first thin film device with an efficiency below 1%. And over the next 12 years or so, the efficiency was improved by about an order of magnitude. And all of this work was done by vacuum-based approaches, such as evaporation or sputtering. And we wanted to see if we could adopt our solution-based approach for doing this. And the problem we ran into was that zinc is not soluble in hydrazine. And so we needed to adopt a hybrid approach in which we first dissolve copper, tin, sulfur, and selenium in hydrazine, and then add zinc powder, which reacts in situ to form these zinc chalcogenide nanoparticles. And you can see what those look like here. These turn out to be hydrazine zinc chalcogenide, which easily decomposes to the corresponding zinc chalcogenide under gentle heating. And so if we take this slurry, we can process it using the same types of approaches we use for the pure solution, and we generate, after heating, our CZTS film. Using this approach, very quickly we were able to get to efficiencies that were substantially better than had been achieved by vacuum-based deposition, around 40% over the previous record. And these were achieved even with films with relatively non-ideal structure. You can see that there's smaller grain material near the back, lots of voiding. As we were able to improve the small grain structure at the back, the efficiency improved to above 11%, so these were the first devices over 10%. The improvement came predominantly from short circuit current and fill factor. The open circuit voltage remained under 0.5 volts. And in fact, if we compare our JV curve for our best device at the time with the Shockley-Kaiser limit, the short circuit current and the fill factor are not doing too badly. However, clearly the open circuit voltage is suffering quite severely. And any attempt to significantly enhance the performance in CZTS needs to address this issue. And as a metric, one can define an open circuit voltage deficit, which is just the difference between the band gap and the open circuit voltage. For high performance CIGS devices, this value is below 0.5. Best devices are around 0.4. For all of our CZTS devices, and we've looked at many thousands, the value is greater than 0.6, often greater than 0.7. So this is clearly something that needs to be addressed. And one of the first areas we looked at was maybe our deposition process is contributing to this. Namely, if we consider a slurry approach, most people who've worked with particles will understand that particles like to aggregate. And if they aggregate, this can lead to non-uniformity in the precursor film and ultimately in the final film. And so we wanted to look for ways of creating a pure solution approach for the zinc-based system. And one approach was reported by the UCLA group, where they reacted carbon dioxide with hydrazine to create this hydrazinocarboxylic acid derivative, which coordinates the zinc and enables the creation of a pure solution. And they were able to demonstrate 8% devices using this approach. We used a similar approach, but adopted a zinc salt rather than reacting the highly energetic reaction between carbon dioxide and hydrazine. And we're also able to create this pure solution, and then we followed the exact same approach we used previously. And using this process, you can see we get substantially smoother films. They're shinier, also more uniform. So these are light beam induced current studies, two different wavelengths for the slurry process and the solution process. And just visually, you can see that these solution process devices look more uniform. This did give some improvement in open circuit voltage, so maybe 5 to 7% enhancement in the open circuit voltage, and so that was encouraging. And combining this with improved light management techniques, such as mentioned in the previous talk, we were able to boost both short circuit current and VOC to yield what is currently the world record for this material, 12.6% devices. And this also gave our best open circuit voltage deficits of 0.62 volts versus the previous 0.67 volts for the 11% device. And so this, again, is nice improvement in the open circuit voltage. Still not good enough. We're still pretty far from where we need to be for the Shockley-Kaiser limit. And the question is, where is this coming from? Interfaces, grain boundaries, bulk defects. And so the first place that one often looks to try and address this is to look at the temperature dependence of the open circuit voltage. If we look at the expression for open circuit voltage, there are two terms. The first is the activation energy of the dominant recombination process, and the second is a temperature-dependent logarithmic term. And so if we examine VOC as a function of temperature and extrapolate to zero temperature, we can get out this activation energy for the dominant recombination process. And so in essence, this is a window into the recombination going on in the device. And comparing CIGS with CZTS, in the case of CIGS, if we extrapolate VOC to low temperature, we get the band gap of our CIGS absorber. And this is what's expected in a well-behaved thin film device. It means we're getting recombination in the bulk of the material. In the case of CZTS, which actually has the same band gap, you could see this extrapolating well below the band gap value. And this is typically taken to be attributed to a dominant recombination loss at the absorber-buffer interface. And this is not something you'd like to see. But it's important to point out that this can be due to other Fermi level pinning mechanisms as well. In either case, this is likely to be indicative or contributing to the low VOC at room temperature as well. One of the reasons for issues with recombination at the interface can have to do with the band alignment at the interface between the absorber and the buffer layer. And for CAD sulfide and CZTS, we have two possibilities. Either there can be a barrier, so the electron affinity of the CAD sulfide is lower than in CZTS, or it can be the other way around, and we can have a cliff at this interface. If we have a spike and it gets too big, this is going to act as a barrier to current transfer or current flow, and it's going to lead to a reduction in the short circuit current, which will ultimately end up hurting the efficiency. In the case of a cliff, the cliff will enhance recombination at this interface and hurt the open circuit voltage, which again will show up in the efficiency. And so ideally we'd like to have a very small barrier or spike at the interface between CZTS and CAD sulfide, somewhere in the range of 0 to 0.4 eV. We've examined this band offset using UPS, which basically measures the valence band offset, and then we use the known band gaps to get the conduction band offset. And for a range of different sulfur to selenium ratios in CZTS, so for a range of different band gap values, we find that our conduction band offset is a spike in a reasonable range. And so conduction band offset we do not believe is likely to be a cause for the low open circuit voltage in these films. Another thing we've examined is grain boundary, the nature of the grain boundaries. And one of the things we found is that air annealing substantially improves all of the device parameters. And we've looked at what is happening compositionally when we do this air anneal using nano-Auger. And the dominant thing that's evident here is that we have an enhancement of tin and oxygen at the grain boundaries. And so we're forming a thin layer of tin oxide at these grain boundaries. And if you also look at the energetic offset of the bands at this interface, you could see that electrons are basically repelled from this interface. And so the grain boundaries are basically there's going to be reduced opportunity for recombination at these grain boundaries. And so the tin oxide can serve to passivate the grain boundaries if it's not too thick. And so these are some of the issues with interfaces and grain boundaries. What about bulk material? One of the things we were worried about was band tailing. band tailing in the material, or states in the band gap, can arise from a number of different factors. One is band gap fluctuations, and this can come from non-uniform composition. And so this, for example, could arise from what I was talking about with the issue with particle aggregation. But also electrostatic potential fluctuations can also be an issue, and this arises from charge defects. In either case, band tailing reduces the effective band gap and therefore reduces the achievable open circuit voltage. Using simple models, one can predict how much these fluctuations will reduce the VOC. Depending on the model, the functional form will be different, but in general, the amount of reduction is going to depend on the amplitude of these fluctuations. So we saw why band gap fluctuations may be important. Why might we have charge defects in this material? This can be examined using density functional theory, looking at formation energies and energetic positions of these defect states in the band gap. And what's clear in these calculations here is that there are a number of defects that have low formation energy. In fact, in this particular calculation, the copper on zinc anti-site defect has negative energy, which would mean it forms spontaneously. And in fact, if you look at the composition of these films using neutron diffraction or resonant X-ray diffraction, one finds that there's macroscopic amounts on the order of tens of percent anti-site disorder between the zinc and the copper. So clearly there's a large amount of disorder in these materials. Likewise, the copper on zinc anti-site defect is deeper in the band gap compared to the copper vacancy, and with a certain high concentration of these defects, we'd expect this defect state to broaden out and perhaps merge with the valence band, creating band tailing. As far as evidence for band tailing in the materials, we can look at the quantum efficiency. Quantum efficiency in the long wavelength regime is proportional to the absorption coefficient, which is in turn proportional to the density of states. So tailing in the quantum efficiency is proportional to the density of states. And if we compare a CIGS-based device with CZTS, we can see that the tailing, or the cutoff of the quantum efficiency at the band gap, is much shallower in CZTS compared to CIGS. Likewise, photoluminescence, the PL peak is broader and shifted further from the band gap value in CZTS compared to CIGS, and this is also indicative of band tailing in the material. From time-resolved photoluminescence, comparing CIGS and CZTS, the lifetimes are fairly comparable, around 5 nanoseconds at room temperature. But if we cool down, fairly dramatic things happen. CIGS is roughly the same, the lifetimes don't change. But for CZTS, we get around 3 orders of magnitude in enhancement of the lifetime. And this we take as evidence, or is indicative of electrostatic potential fluctuations. Namely, if we lower temperature sufficiently, photoexcited electrons and holes will get localized into pockets which are physically separated, and therefore reducing the opportunity for wave function overlap and likewise the opportunity for recombination. And so we propose that these electrostatic potential fluctuations and associated band tailing are responsible for the bulk of the VOC deficit issue in this material. And this can be incorporated into a device model. So in this device model, we can completely account for open circuit voltage, short circuit current, fill factor, efficiency, as well as a host of other measurements that we've made, including the depletion width and diffusion length, lifetimes, mobilities, band gaps, our VOC versus temperature results, which I showed you. But the important point is that we're not introducing any problem at the interface in this device. So device interface recombination is not necessary for explaining these parameters. Rather, we're introducing this electrostatic potential fluctuations by the introduction of a mobility gap which is smaller than the optical gap in the material, or the band gap that we get from the EQE. And this is what's responsible for the reduction in the open circuit voltage. This band tailing also accounts for the tailing in the absorption coefficient that we observe. And so with this, again, this points to the fact that bulk tail states are important in terms of trying to reduce the open circuit voltage deficit. The problem with this, from a device person's point of view or a materials person's point of view, is that this is harder to solve than, I think, the interface problem. And so this is a little bit unfortunate. On the other hand, there are some promising recent developments. The first is some work from the Angstrom labs and others, where they were looking at first a way of characterizing the disorder. And in this particular case, it's characterized using near-resonant Raman scattering. One can define an order parameter, depending on the intensity of certain peaks in this resonant Raman scattering spectra, which characterizes the degree of copper-zinc ordering. And what they measured, or what they distinguished, is that there's an ordering temperature at around 530 Kelvin. And below this temperature, the copper and zinc starts to order. The problem is this is a relatively low temperature, and so the kinetics of ordering is relatively slow. And so depending on the cooling rate, you'd expect to see some peak in the ordering with the height of this peak, or the degree of ordering, depending on the cooling rate. And this is something that they actually observed. The problem is that so far this approach has not led to better device performance. One thing that has led to improved device performance is this experiment that we did here, where we incorporated a thin indium sulfide film on top of the cad sulfide, subjected the film to a brief anneal, which diffused the indium into the cad sulfide and CZTS, so our intention was to dope these layers, and this led to a consistent reduction in the open circuit voltage deficit for a range of different bandgap values for the CZTS. And this led to our first devices with a VOC deficit below 593 millivolts. And so there is some promise there for reducing the VOC deficit further. And so to conclude this aspect of the talk, I've described a solution-based approach for depositing high-performance CIGS and CZTS devices. I think what's really exciting about this is the fact that usually solution-based deposition is thought of as an approach for low cost at the expense of performance. Here we see that high performance can also be achieved using solution-based deposition. Some of the advantages of solution-based deposition include mixing on a molecular scale, which enables lower temperature and quicker processing. The incorporation of impurities is also very easy, which can control grain growth, and the processes can be quite high throughput. In the future, for CZTS to become a competitive commercial possibility, I think we need to get to efficiencies over 18%, and to do this will require a better understanding of defects and bandtailing in this material. And in my own case, I'm also interested in designing and fabricating new semiconductors where we use what we've understood or learned from CZTS to create systems that have less propensity toward anti-site disorder. And so with that, I'd briefly like to mention the other very promising solution process semiconductor, and these are the perovskites. Our interest in this started back in 1994, where we were looking for solution processable semiconductors, low temperature solution processable semiconductors, and we decided to look at metal halides. Metal halides are usually pretty poor conductors, but this family here, A'2, An-1, Mn, X3n plus 1, where A' is a large organic cation separating the perovskite sheets, A is a small cation within the perovskite sheets, M is, of course, the metal, and X is the halogen. N refers to the number of perovskite sheets between the large organic cations. If we use germanium, tin, or lead, we have this unusual case where we can get semiconducting metal halides, and as the dimensionality of the perovskite framework is increased by increasing N, we go toward progressively more conducting and even metallic character in these films. And this is exciting because it means we have a highly tunable, also solution processable at near ambient temperature semiconductor. The n equal to infinity compound that I'm referring to here is just the cubic or three-dimensional methylammonium lead or tin iodide material, which is the one that has generated a substantial amount of excitement because of the very rapid rise in efficiency that's been possible in this field of photovoltaic. So currently above 20%. What I'd like to highlight also is this very low open circuit voltage deficit, which, as we heard for the other solution process semiconductors, was a problem. And as we've learned more about this perovskite absorber, the role of the absorber in the device structure has shifted from being strictly just a dye substitute or an absorber to playing other roles in the device, including acting as a charge transport layer as well. And the reason for its high performance or high suitability for PV relates to, first of all, it's got a direct band gap, but also the nature of the states close to the conduction and valence band edges is P-like in character, and this gives rise to a large joint density of states, which in turn leads to high absorption. And as we heard, this enables the ultra-thin absorbers, meaning that the photogenerated carriers do not need to travel very far. Also, a high degree of sp coupling enhances the dispersion of the upper valence band, which means that not only the electrons but also the holes can have a small effective mass and high mobilities, and this contributes to long diffusion lengths in the device. Additionally, if we look at defects, the dominant defects are very shallow, and so this contributes to not much recombination and therefore higher VOC. And likewise, the grain boundaries are predicted to be benign in this material for similar reason, namely grain boundaries locally can look like interstitials or vacancies. And so this, again, gives rise to the high open circuit voltage. And then finally, as we heard in the talk yesterday, these are very simple materials to deposit. They essentially self-assemble, and this is associated with the very low formation energy. Basically, they can be formed at room temperature, and this opens up opportunities for spin coating, melt processing, evaporation, two-step dip coating, etc. And so I think this is very exciting. I won't go into it in more depth because it's already been covered, but I think in the future it's important to target higher efficiencies. Of course, we need to look at the issue of lead use. Can we replace this with less toxic metals? There's the issue of stability, hysteresis, and I think ultimately this comes down to understanding not only the bulk of the material, but also the interfaces in the device. And so, again, the perovskites are another example of where solution process devices have yielded the highest efficiencies. And so overall, I hope I've convinced you that solution-based processing offers a number of opportunities for lower cost and high performance solar cells, and also offers great interest in terms of the science and engineering that can be accessed. With that, I'd like to thank you for your attention.
Thank you very much, David. And with that, I'd like to open up the floor for questions.
I have a question. You showed in the first graph that impurity has an influence on the CIGS structure, crystal structure, but you didn't mention anything for the crystal, right? Do you have some experience on that? The second question is, did you make some experiments on using natrium, and how is the influence on that?
Perfectly combined question, because I was going to bring up the sodium as well. In CIGS, both sodium and antimony can impact the grain structure. Sodium is known to be important also decorating the grain boundaries as well for reducing or improving the performance of the device. In CZTS, the impact of antimony was less clear in terms of affecting grain growth. Basically, if we had sodium already in the film, adding extra antimony did not further improve the grain structure, whereas in CIGS, there would be an additive effect. In CZTS, sodium or antimony were needed in order to be able to improve the grain structure of the device. So in none of the records that I showed were we intentionally incorporating antimony in the device, but there was sodium, generally from the substrate, but we also added ourselves if needed. So sometimes we put down barrier layers and then we'd add the sodium.
So in the
up the slide showing defect energy level versus which defect we're talking about. Some of them are quite deep. And I think the reason that the way I describe it is consistent with the notion. And basically it's taking the evidence more broadly, looking at photoluminescence, looking at quantum efficiency, the absorption data. This is the reason for, as well as the actual understanding that discharge defects are expected in the material. So there's no particular reason for excluding the possibility that heat defects can also be contributing to this effect. I think one other point I'll make is that CIGS also has heat defects, such as those gallium on copper defects, and there the band scaling is not as, this lifetime effect is not observed.
You mentioned that the interface layer still got cadmium in it, cadmium sulfide. You mentioned some alternatives to that. How much progress has been made with cadmium-free interface?
Quite a bit, actually. I mean, in Japan, the sensitivity to cadmium is very strong. And so one of our partners, Solar Frontier, has a business gigawatt production facility based on 6 solar cells with a zinc-based buffer layer in the device. And working with them and also on our own, we've explored the zinc-based buffer layers and have seen not as good performance, but quite good performance, almost as good, let's say. Predominantly, the reason I don't mention that much during the talk is I can't give as many details, and so, but yes, there is work on those other buffer layers.
You showed a graph of VOC as a function of temperature, and one of the curve was coming down.
Yes.
Is it,
So, yeah, let me just go back to that quickly. Oh, there it is. Yeah, so this type of behavior, we've actually done full studies of VOC versus temperature versus sun's intensity. And basically, if you look at VOC versus sun's, unlike the light intensity, unlike in CIGS where the VOC will monotonically increase with sun intensity, here we actually see a rollover behavior and it can actually come back down again. And likewise, with lower temperature, this behavior is made worse. And this can arise for a number of reasons. Amongst them can be a non-ohmic back contact, so an inability to get charge out of the device. I gotta think back to the other reasons are. I'll get back to you on that in just a second. My brain is. But there are a few other reasons where that arises.